Today we're going to talk about microservices, and the first lesson that I learned bringing this talk together is that you never should bring a number in your presentation title. So we're going to discuss 6 instead of 5. So a little bit about myself. You can find me on Twitter on @Vincent Kok. I'm Dutch. I work for Trello. Who is using Trello in this room? Quite a few. Who's using any other Atlassian product in this room? It looks like an engineering conference to me. So the only thing you have to remember about the slide is where you can find me on Twitter. Feel free to reach out after this session or during. I won't reply. We're going to talk about microservices today. And for some reason, everyone wants to have them. And still after a few years where everyone is talking about it, every time we go to a conference, it's still an active subject. So why is this so important to us? Why do we all want to try out this architecture? Well, it gives a lot of problems as well. So if it gives us something, it must be solving something, right? So what kind of problems do we currently have? And this is what happens a lot when you work on large applications. And I know there are some architects in the room. Sorry for that. I'm not sure where your name is on it. Jokes aside, when you work on a large application that has been evolving over the years, you have a lot of issues, right? First of all, they grow fat over the years. So adding changes becomes harder and harder. Builds become slow. Your IDE is not as good anymore because it just takes a long time to reindex. And builds just takes longer. They grow old as well, so you pick a technology. Like today, you go to a conference, you see something awesome, and then you're, oh, we're going to use it. But after a few years, something new pops up, and adding that into your landscape becomes harder and harder. If you look, for example, at Confluence, we even have webworks still on, so you kind of see all the frameworks over the last 14 years in Java world. They are in the code base. Ownership becomes an issue as well, so who is owning which piece of the code? It's really hard to define it. You can do component ownership, but it's too hard to fit in everyone's minds. And at some point, when you grow larger as an organization, you're not independent anymore. So if you're working on multiple teams, people will step on each other's toes and slow each other down, which is painful and makes developers unhappy and slows your business down, basically. So let's have a look at Atlassian, a few examples why we thought it was a good idea to actually start to decompose our applications a little bit. So this is an example of Confluence where we run around like 8,000 jobs a week. This was from a while ago, but it's going faster and faster. So we need a lot of infrastructure to actually maintain it. We actually have a separate team to maintain all the build infrastructure. And we run all those tests for even minor changes, so it's kind of wasteful. We have around 32,000 automated tests. And if anyone did some automated testing, especially on higher levels, it becomes harder and harder to maintain. And there's nothing such painful thing if when you change a comment in your code and your build goes red and some test fails, and that happens to everyone, I think. So it's good to have many tests because you know if it's green, it's probably pretty good, but they're painful and hard to maintain. Or what happens if you get a regression in production? Suddenly your response times go out of whack. How do you deal with that? Who caused it? You go back in the commit tree, and you see many, many changes, so who was the culprit? And this is probably my favorite one. Who is having a pager? Because I think nobody in this room likes to actually being woken up in the night, so this becomes really painful because like you wake someone up, then suddenly you figure something out, but you need another person, so you need wake another person up. So it's impossible for one team to actually maintain everything in one team. I want to give a bit of a warning as well, because like the tendency there is, like if you go to conferences, you learn about new things, like you want to try it, but there's always important that you actually figure out, hey, do I actually need this? Because we're not all web scale, right? So if we build a simple application that doesn't get a lot of traffic, just keep it simple. Because normally you hear a lot of cool stories from companies like these, and if you look at these numbers, this is an internet minute in 2017, these are crazy numbers, and not many of us will probably have those. I read a blog a while ago, and Dan Noor was basically discussing some things, and he said like it's responsible for engineering teams to optimize for a sustainable flow of value. So I think as an engineering team, it's really important that we actually drive for value. That's the reason why we're there. We have to do it in a sustainable way, so we can't continue to keep cutting corners all the time. So we have to find a way and balance how we architect our application. And that's how we have a value at Atlassian where we say we build with heart and balance. So trying to keep speed and value and keep them in balance and not go too crazy, but sometimes you need to make big choices. So why does one want to do microservices? for a few reasons, right? Obviously they're small. And I personally don't care too much about the actual size. But I think it's important to keep in mind that they fit within one team. If one team can't own one service, then you know you're in a problem. Because then you get the same issues again when you had your monolith again. So if one team isn't able to actually own the service, then you're in deep trouble. The other thing is like, you want to have an independent lifecycle. You mentioned already, hey, teams are stepping on each other's toes. This will basically solve this issue. Like a team can go as fast as they can based on the skills they have and based on the tools they have. So they can't do any finger pointing anymore. Then it won't be blocked, there won't be any frustration anymore because they basically have to look at themselves and see, hey, what's going wrong and how can we fix this issue? You can also optimize for the problem. If you have a different need for a certain issue you're trying to solve, you can pick different technology. You can even pick a different language. A word of warning here, if you go nuts with all your technology, it becomes really hard to actually transfer services to another team. Good example, we have a service that's written in Clojure. We have basically one team who's able to maintain it, so that's painful. It was a good choice from the problem perspective, but it can be a bad choice organizationally, so keep that in mind. We try to stick to a few frameworks to make it easier to transfer service between teams, if that happens. And the last one is like they are replaceable as well. If you have a large monolith, replacing it into a new technology becomes really, really hard, right? Because you can't just rewrite it overnight. And I'm not saying like it's really easy with a service, because you probably won't be doing rewriting service all the time because you want to create new stuff. But it's an option. We did it a few times where we picked the wrong language, so we picked the wrong tools, and for the team it was a better fit to actually rewrite it. So it's an option. And it's not a massive, risky project anymore as it would be with a large application. Okay, let's discuss a few patterns. I want to go through the basics real quick. Then we're going to talk about deployments, testing, security, operations, and the bonus one is decomposition. And for you, I just want that you take one home. That's it. If you remember all 6, that's high five. But if you just take one home, that's cool already. So let's go through the basics, basically the salt and pepper of microservices. Who's familiar with the 12-factor app? That's quite a few hands, that's good. And I think this has been written like in 2012 or something like that, but it's kind of like, hey, what's a good application which you run in a service-oriented architecture? And it says quite a few things about how you do configuration, how you set up your process and stuff like that, how you deal with logging, et cetera, et cetera. If you Google 12-factor, you will find it as the first hit on Google. So have a read and see how well your application fits. For us, we translated it like, what's a minimal service, right? And it's fairly simple, to be honest. We have had to expose a port, probably HTTP, via Tomcat or whatsoever. We have a health check to see whether we should kill the instance or not. And it should be stateless, because you want to scale it out. But be aware, like, not all services are going to be stateless. Sometimes you need state for performance reasons. Keep in mind, if you have state, you have to be able to survive like a node crashing and another node can take it up. You might have a performance hit, but that's all right. The other one we add to a service is deep check, and a deep check is a little bit slower, a little bit deeper than a health check, and it basically checks the dependencies as well, so you can actually see, hey, can I still talk to my database? Can I still touch a service I depend on? We have some debate internally whether this one is a valid one, because if you have all monitoring right, you probably won't need this, but it's very valuable to figure out, like, hey, do we have any configuration issues? Do we have any networking issues? And you get some more insightful alerting there, which is good. This is a little example of a deep check. It's just a JSON blob where you say, hey, these are the dependencies we have, and how is the status, and are we still running all right? Code and builds, we try to keep it simple as well. Some companies go for a big monorepo, but you need a lot of tooling to keep things independent as well. So we basically say we have one repository for a service and we have one build. And we try to repeat that pattern for every service, so it's easy to go in and see, hey, this is how I deploy it, and that makes it easy. So you don't have to set it up again all the time, because you just have it in place. And the biggest and the most important thing is you have to keep them decoupled, right? And if you start to couple them again, then you basically get like a service or a set of services that are still attached to each other. So you lose all the value of microservices and you only inherit the problems they give. A lot of people actually say, hey, you shouldn't use any shared libraries for microservices. I don't think that makes sense, because you want to share code between them. Otherwise, you keep on repeating a lot of code, which has its own problems as well. I think it's important that you can continue to deploy services independently. If you do a bump of a library on one, you shouldn't be automatically have a bump in the other library. So that's probably the thing to keep in mind. The other thing is around schemas, right? You don't want to have any dependencies between schemas or services. So again, like some people prefer client libraries, some people do not. But if you make sure they're flexible and they stick to posters law, so basically be conservative in what you do and be liberal in what you accept from others, then you can go a long way to prevent like having decoupling on API level again. The same for testing. When you go for testing, the first thing you probably do, okay, just have like a Docker, do a Docker Compose, spin up all my service, and run an integration test. It will probably work for a few services, but it won't scale indefinitely. So you have to come up with a strategy there. We will talk about it a little bit later. And the last one is configuration. And I want to dive a little bit deeper in that because you have to be aware of your configuration lifecycle. If you look at the 12-factor app, it basically says you have to have strict separation of configuration from code. And you have tools for that support it. For example, you have Puppet. But the problem with Puppet is that it creates a new lifecycle again, which can be painful. So did you know your Puppet run finished, and can I actually deploy it? So I'm not a big fan of those tools. So what kind of life cycles will you incur? So I think there are three life cycles you want to have. First of all, like you have like configuration is not too important for you, and you just basically say, I do a rebuild. I have them in my source repository or in a different file. That's probably fine. So you rebuild to apply those changes. It will be slower, but if it's not changing too often, then it's good. You can have configuration that's part of a redeploy. So if you redeploy your service, then they will get into effect. Think about environment variables. That's what you use a lot for most configuration. And then you have configuration where you want instant change. For example, if you want to toggle features, or if you want to kill a feature. For example, you have an email feature in your application, and it goes haywire for some reason. You want to kill it for a while and figure out what's going on and not spam everything and get issues with your email provider. One other note on services that you have to treat them as cattle and not pets. And what I mean with that is, or actually what Bill Baker means with that, is that you actually don't get attached to your service. You don't name them, you don't give them like a number. They probably have a number or even a UID, and that's about it. So if they start to misbehave, you kill them. So it's a little bit harsh for thinking about it as cattle, but it's kind of like, you know what I'm saying. It's not like a pet where you get really attached to, and it will live for a long time, and it will be a buddy. It's like something you keep in a distant future. In a distance, and actually when it's not there anymore, you don't care too much. I'm not a farmer, by the way, so I don't know. Okay, those are the basics. So when you have like your pattern, like how you want to build out services, you have to start deploying them. And it's really important that you get really good at it because you're going to do a lot of deployments and you're going to deploy a lot of services. So how are you going to do it? So let's do a little game here because it's still early. People had just their first cup of coffee. Everyone who requires a ticket to deploy something in production, please raise your hand. Oh, it's not too many. Keep your hands raised, okay? Anyone who has only one person in the team who can do the deploy? Oh, that's only one. You know, just well, very good. And any people who takes more than 50 minutes to deploy into production? There are a few more hands. Like, okay, you're an honest audience. I was starting to doubt a little bit, but that's good. So I think it's really important that you have these things in place. If you require a ticket, then you will be in a world of pain. When we started to do service, we at some point realized, hey, I want to try this out. We don't have a platform to actually deploy it. So how are we going to deploy? So we created a ticket, had someone build up an Amazon stack, and then it just took too long. And then you can do one, but after the second, people will become miserable and will become very painful. And the same if you have one person in the team, then you have a dependency and probably a liability and a big buzz factor there. And you want to keep them quick as well, because that's just nice. So what we try to do when we start a new service, we always deploy an empty shell into production. So basically say, hey, the basic we just said, we have a port, we have a health check. That's basically an empty service. You can use Spring Boot, which we like to use a lot. You can generate a service fairly quickly. Get it into production. It's basically hello world, but you know your pipeline is in order and you don't have to worry about it anymore. So then it's like, how fast can you iterate on the functionality of the service, which is quite nice. So you don't have to worry about that anymore. And you want to have developers in control. So if you need someone else, then it will be a slowdown and you lose that autonomy. So what kind of control do you need to give that to the developers? First of all, what artifacts need to be deployed, right? How much compute do you need? What kind of ownership? And ownership is an important thing here because, like, for example, if you want to bill to your department, like who's paying the bill for whatever compute you're using? How do you deal with resources? Hey, I need a certain queue, I need a database. I want to have alarms because if something goes wrong, I want to get someone woken up because I want to take action. And the last one is configuration. So how do you deal with configuration? We already discussed the configuration lifecycles before, and that's what you want to have put in place. So you can go for, I just use, for example, Amazon CloudFormation, but that's kind of a steep learning curve, and that's hard for a development team to grasp, or you need to skill them up, and you probably need to skill a lot of persons up. So we went for a declarative approach. It's just a YAML file where you can state all those things. We built a little platform initially, which was really lightweight. We called it Micros. It's a very, very interesting name. And where you can basically declare all the things you need. So it's just a simple file where you say, hey, this is the binary. It's a Docker container. This is where you can find it. We have a health check and deep check, so basically all the basics already discussed. That's kind of the pattern we reapply. And this gives the development team and engineering team the power to actually, hey, this is what I want to deploy, and just push it up. And the machinery behind it basically does all the hard work. And it's nice because it kind of gives a contract between the engineering team and the team that actually has all the compute available. And it doesn't matter if it's Amazon, you can pick whatever you want. We decided not to go for things like Cloud Foundry because it was too strategic for us to actually say we want to pick one framework. So we built a lightweight wrapper ourselves. So it went a long way for us. We still have it in place. We have a fairly large team working on it, but with the rise of Kubernetes and Amazon still being fairly slow to actually spin up new instances to auto scale, we're moving into that direction. But the good thing is, actually the contract to the service remains the same, so that's quite nice. We also made a deliberate choice to actually not care too much about having a leaky abstraction here. So you will see Amazon terminology. For us, initially we said, hey, we want to abstract it all away. But then again, you want to deliver value, you want to be fast as well. So we said, like, we don't care for now. We're going to place a bet on Amazon, and we'll figure out later if that's not the right choice anymore. This is how we define configuration as well. And this is here, you see, like, probably a good example of the 12 factor app, where you have your configuration in a separate file, and the code only knows about environment variables. And if you deploy a service, you pass the file like this, and it's part of the service script, and you basically run it into production fairly easily. The same for resources, right? You want to be declarative in your resources as well. Like, for example, you need an SQS queue, and you also want to say, I need this type of compute, and you want to have teams give the teams the ability to play with the compute they need. Sometimes you think, oh, I'm going to go with this, and then you see response times going up at peak hours, and you can just switch it quite easily. And a feature we added recently is quite neat, I find, is sidecars. Does anyone in this room knows what sidecars are? A lot of people. So it's basically you run a separate service next to your microservice and you put some functionality there. For example, you want to do something with an outbound proxy with a circuit breaker. So basically you want to have that in one place and you don't have the libraries in place, or you have too many different languages, so you have it in one place. So you can put it in a separate process. And because it runs in the same container, the latency is still fairly low. So it's quite nice and quite neat, so you can run helper processes next to your process for a certain thing. There's an example of an HTTP frontend that was really application specific to actually do so, which was cool. So far, we have around 500 services in production, which is a large set, and it's growing basically every day because every engineering team just can push it out, and based on the declarative deployment, they can actually say, hey, I want to have that in production right now, so teams can go as fast as they want, and they can make picks what suits their needs, so giving a real autonomy. So let's discuss testing, and testing is always an interesting one. Because if you look at testing in microservices, it looks a little bit like this. Because if you look at testing monoliths, it's fairly easy. Maybe that's a bit of an overstatement, or like I'm just trying to make a statement here. If you're struggling with testing your monolith, it becomes even harder. So that's kind of one of the costs you get when doing microservices. Like, you have to think about your testing strategy. And normally you look at a testing strategy like this, right? So you have a unit test, you have integration, you have UI test, or a pyramid, and the shape depends a little bit on where you're at in your organization. Sometimes the UI is a little bit wider than you want to admit. But everything above unit test becomes an issue with microservices, because suddenly you have dependent service, you have services where you depend on it. That can be pretty tough. So how do you want to deal with that? You have a few options here. Like, I think the easiest one I already mentioned is like you just test against a live service. And that's fairly cheap, because it's already there. You probably have like some staging environment. The problem is you create a dependency with another team again. And when they do a test by themselves, or they're just trying out new code, your tests suddenly become flaky. And if you want to do local engineering, then it becomes harder as well, because suddenly you have to run it locally as well. And what if their API consists of many, many servers as well? So you can use Docker to the rescue and compose all the things together, but you probably need more than a laptop at some point to run that, and a lot of memory. The other option you have is basically say, I'm going to use a mock service, and this is the one we prefer, and actually like say we never test against real dependencies, and pick a mock service, and this is where that's what replies to your actual service. You have two options here to actually do it. You can do it in process, and you have a local implementation or stub of your service, or you use an out-of-process service like a YMock. We tend to use YMock quite a bit. We didn't do a deep study on like YMock or other, because there are more tools available like mock server, but it actually works really well, and we kind of like we liking it. This is an example of how you could do an in-process. This is a Spring example. I'm still maybe a little bit getting old. I like XML. Most people don't, but you can use Spring Proofs and actually say, whenever you spin it up, this is what I want to reply. I think the big problem with this is like you're slowly leaking some test information into your code base. You can keep it separated, but your code starts to know about testing, which I like to prefer to actually keep it out of it. The other option is using YMock. In YMock, you basically have an out-of-process process running, where you define your request and your responses with a JSON file. And it's actually pretty good, because the good thing about this is really easy to model error situations as well, because the testing the happy path, that's always easy thing. Your service will probably respond. But how does your service? That depends on many other services on error responses. This gives you actually the ability to actually define this and see how your application responds, which is neat. And because it's out of process for your own application, for your own service, it doesn't matter too much anymore, which is kind of neat. But you run into another issue, right? So how can you trust your mock? And that's an interesting one. So there are a few options there. So you can say, hey, I rely on my monitoring. If you have the right monitoring in place, it doesn't matter too much anymore, because you can basically say, hey, if something goes wrong, I send out to a small canary release, and I just roll it back as fast as I can, because my pipeline is pretty sweet. You can do it. It depends on the risk and depends on the impact of when things go wrong. You can focus on having a stable API. If you have third parties using your API externally, then you probably already have a CDK in place and basically say, I'm pretty sure my API is stable and I rely on that. That's an option as well. And I think we do it for quite a few APIs internally. And the other one is contract testing, and that's kind of like the new-ish kid on the block, but it still has quite a few problems, actually. For example, you have a few frameworks that are quite fairly young, and it's actually a bit harder to define them, and it requires a lot of builds from all sides. So currently, we experiment a little bit by using Swagger to actually generate contracts based on the Swagger definition. It's still early days for us, but basically getting rid of all the manual stuff. And based on the contract you provide externally, we're going to build testing as well. And you can actually say, this is how we make sure our contracts are still valid. The last one is semantic checks. And semantic checks is kind of like the last line of defense we use, and of which I'm not a big fan of, to be honest. And semantic check is basically a small smoke test that runs before we put the service back in the load balancer. Good thing is like it catches a lot of like last minute things, or if a third-party service screws up. But it's really late in the game. You add additional slowness to your deployment pipeline, which is not a lot of fun. So I think we should get rid of it, but it's an option if you want to have a last line of defense. Cool. Let's discuss security. Security, there are quite a lot of open standards in the web community, right? So we have OpenID, which is fairly old already, not very commonly used anymore. We have OAuth, which we probably use every day. And there is OpenID Connect as well, and OpenID Connect is kind of like OAuth with identity attached. And they're all kind of neat for their purpose, especially if you look at OAuth 2 and OpenID Connect. But they don't solve the problem if you want to secure services that communicate with each other, because that's not what they're designed for. It's more like user interaction. The big question is, how do you secure a set of many services? You can actually say, I just rely on my network. I just have a big black box, and everything inside is safe and secure. But if your service starts to grow, and even if you have like service that expose financial data, that becomes harder and harder to maintain. Or if you use a library that has a server-side request forgery issue, then suddenly you expose all your service. So that's kind of like an easy way to get out, and probably not the safest one. We couldn't find a lot of stuff around. There wasn't too much chat about it on the internet as well. So we came up with our own authentication protocol. And I know you're thinking like, hey, those guys are creating their own security protocol, way to go. That's not what we did. It's based on standards, and it's actually fairly lightweight as well. So how it works, if you have two servers calling each other, we have a signed JWT, and that basically makes sure it gives the receiving service to actually see whether that service is allowed to call them and whether all the data is correct. So let's have a look. Everyone familiar with JWT? Most people, or quite a few, that's cool. It's fairly easy, just a base 64 string and defined in three things. You have the signature, which I got out because it's a bit long. You have the header, and you have the footer. I left out all the JWT stuff, and this is kind of the stuff that's important for the service, right? The first one is really important, which is the key ID. This is kind of like the identifier of the service calling, and basically this is how we can look, the service receiving the call can look up the public key of the service that it signed the message. So that's kind of a convention we have. We have a key server that actually has that information. The information below is interesting. So you have the issue, which is the service calling. You have the audience, which is the service receiving. And you have the subject, which is kind of the identity of the user calling that made the first call. So you can actually push through the identity of the user calling if you want to do user-specific stuff, which is quite neat. And because JWT is kind of like an accepted standard, it's fairly safe. And it's low overhead because you can do some key caching as well. So it's fairly quick, and it doesn't need a lot of CPU. You can try it yourself. It's available on Bitbucket. So have a look. We have libraries for the most common languages, which is Python, Java, Node, and Go. Give it a go. Give us feedback. We'd love to hear from you what you think about it. Okay, let's have a look at operations. I want to do a little quiz. This is the American version of the quiz, so you can replace pounds with kilos if you like. So what if you have 100 pounds of potatoes and you dehydrate them to 98% of water? So they go from 99% to 98%. Any takers? No. That's good. Awesome. This is what happens too. So it's called the potato paradox. You can Google it, and it's kind of like the math is all solid. You basically go from a 1 to 99 ratio to a 2 to 98 ratio, which basically makes it 50. The same applies to services, right? So any takers, if you have 30 services working together and they have 4 nines of uptime, which is a downtime of a little bit more than 4 minutes a month, if you look at it mathematically, how much downtime will you incur? Any take? Sorry? A lot, yeah. It's 2 hours. So basically, you're doing all the best to get your service up and running, but you're suddenly sitting there with 2 hours of downtime. So that's the problem, right? Because your customers or your boss won't like you for that. So you have to take care of it and see, hey, what's going on and why is this happening? So failure is imminent in a service architecture. And it's interesting, actually, to see if you look at Netflix, for example. If you look at Amazon, they only provide 4 nines and a 5. Whereas people are building platforms on top of that 4 nines and a 5 that have a lot more availability available. So it's actually interesting to know how do you architecture the thing. So you're not necessarily restricted to the platform you have to get more availability. It's just how you architect your application. And you can do things like multi-region or be very picky on what you return if a downstream service fails. You might not load those attachments if you don't have to, if the service is failing. But you have to take in mind, and keep in mind, what I'm going to do in this error situation. So, and a few things are actually things. Sometimes you can start doing it, and you can think you can skip on things. And I think you shouldn't skip on those 3 things. First of all is log aggregation. There are many, many tools available to do so. It's part of the 12-factor app. Just stream your logs to Splunk or Logstash, or whatever you want to use for it, and make sure you're a happy man so you can actually find your logs quite easily. The second one is circuit breakers. So what are you doing in failure? Because certainly you have a lot of networking involved. And we all know distributed computing is hard. We tend to forget it, but it's still hard. And the last one is request tracing. So how do you debug a trace that goes to many, many servers? Because it gets complicated quite easily. A little confession here. Here's an actual screenshot I made, I think 3 years ago, and this is how I was debugging my system. This is kind of like 8 terminal windows and figuring out what was going on. That's not a great situation to be. So if you're there, get out of it. This is how it looks now. We use kind of Splunk to do most of the log aggregation, and the good thing is, like, engineers can build the most amazing dashboards they want. So basically, you move all the information to those engineers, and you create great insight into your system, and you can basically start tweaking based on that. Circuit breakers as well, and I think Netflix has made them popular. And initially think like, I don't need it yet because I can do it later, or you think, hey, we're not that big. If you're not that big, don't do microservices. Because they're there for an important reason, right? First of all, you want to know how much you spend on calling each service, and circuit breakers, if you instrument them, it already gives it almost for free. So you get a lot of information about your system, like what's going in and out, and how much time do you spend calling other services and waiting for other services. And when do you see spikes, like when do they become slow? And when they become slow, at some point, the circuit breaker will basically go open, and basically you stop putting out traffic, which is good because you want to stop putting pressure on a system that's in trouble. But normally, if you don't think about it, you just keep on hammering the system and the situation gets worse. And back pressure itself is a hard problem as well, because what if you wait and suddenly it comes back and everyone starts to have a reconnect storm and you bring the service down again. So you have to think about it. It's not like an easy problem. And the last thing I basically already mentioned, you want to see how you want to deal with fallbacks, right? So how do you deal with handling failure? And that should be part of your programming model. So if you do a search and your search provider is down, what do? Do you give a nice error message, or do you error out to the customer? So how do you ever deal with that? And that's probably what it all gives you, and it should be part of your programming model. This is a good example of circuit breakers, where we actually instrument them. We get a lot of information. It's probably hard to read from the back or even in the front, but you can get a lot of insight about your system on how it deals as a networking, a set of services running over a network. Last one is request tracing, and I will go through this quickly. I think it's been made popular by Twitter and Zipkin. Uber just released its own version called Jaeger, and it's kind of like very easy to figure out like what's going on. I think the biggest problem with that, how it works is actually you have a trace ID, which goes all the way, and you have a span ID and a parent span, so you basically see what's like my call side, but then on a distributed level. And the good thing about it, you can actually figure out what's going on. The problem with it is like you generate a lot of data. So what people normally tend to do, suddenly you start to sample it. And the problem is like, hey, you have an error, you see the trace ID, and you go to this UI and you can't find it. So data will become a big issue here, because you can imagine you will generate a lot of traces if you have a lot of traffic. This is the UI from Zipkin, and you basically see what's going on if you enter a trace ID. You can see where you spent the time and where it went wrong, and what the payload was. Final on operations. So how do you deal with operations? So if you look at a monolith, we're all familiar with DevOps because that's been going on for a long time. But doing DevOps on a monolith is pretty hard, right? Because who is dev and who is ops? And who do you call when something goes wrong? Because the size of your application is just really, really hard to actually deal with instance, because you probably need more than one brain to actually resolve it. So you probably end up with a large team sitting together if something goes wrong, which is fine during business hours, which becomes a lot harder during the night or during holidays. And even when you start sort of ops, you normally start to enter like a team that starts to receive the call first. You still have like that little opsy teams that now called the DevOps team or the SRE team, that's still getting all the hit without a lot of empowerment to actually fix the system. So that's why we have like the mantra, when you build a service, you run it as well. So we try not to have like an operational team. So if you build a service, you own it. So you get the pager in the middle of the night, and you have the responsibility to maintain it well. And that makes it really clear as well, like who to page. But also when you have multiple services, because probably at some point you stop engineering on one service to actually say which team owns which set of services. So a team can own multiple services. It probably has to do some maintenance on them, but it's very clear who owns the service and who gets the pager. And when it happens, then the team has enough empowerment to actually make the fixes, because I think it's a good driver to make change and increase quality if you get 3 calls at 3 a.m. in the middle of the night. All right, number 6, the bonus one. How are we all doing? Still here? Cool. I think starting to decompose it kind of starts with a statement. And I think we struggled for a long time to actually say, hey, how are we start to decompose this big thing? It's kind of like a scary project, so how do you deal with it? And at some point we said to each other, the monolith is deprecated. We're not going to make big changes to it anymore. And it has quite a few implications if you do so, but that's where you start, right? So you want to say, hey, this is what we see is good for the company, so that's what we're going to do. And we have to figure out what it means when we start a new feature. So a few examples from Confluence. And if you look at what we did initially for decomposing, we took the easy bits. For example, start with the platform service, because they're kind of hidden and under the cover. Not a lot of user-facing stuff. For example, you have a scheduler. Every application is a scheduler. You have attachments, or operational transformation, what we used to do, collaborative editing. Those are the kind of features that are under the hood and are easy to push out. And the second one, which actually being talked about in the keynote, is actually you have a front end. So that's one that's easy to push out as well. I don't know many front-end developers who like Maven. I actually don't know many Java developers who like Maven either, but it's something. I see at least one, that's awesome, we should chat. But it's kind of you want to give front-end developers the tools they want to have and to give them their own lifecycle and just say, hey, you don't have to worry about that scary backend anymore. You can use the framework you want to use and the framework that's hip at the moment as well. So that's cool. So those are the easy bits. But then, how do you deal with core functionality? How do you split it out? How do you move forward with that? As a kind of a strategy, we said we want to focus on ownership. Like we say, we want to have one team that's owning all the code, right? So we want to have a team responsible for the code. So that's it. You need one team. You want to have a team that's responsible for the pipeline. So if something breaks, that's where you look at. And we want to have a team that's responsible for the instance. So just one team. So if you build a feature, you want to have a team that will build a feature and bring it all the way to production. And so you can create a true autonomous structure there. So let's have a look at this core functionality here. So this is kind of like Confluence. It's like the monolith, having a web client, having a mobile client. And first of all, we said we're going to move the monolith aside. We don't worry about it anymore. It's deprecated. We're not going to invest in it anymore. Then you probably want to have something in place, because all the changes you're going to make on the front end, because your client's probably going to move in a different pace than your backend, or you're going to have a little bit in parallel. You want to basically have a proxy in place where you say, this is where you start talking to, and that hides kind of the complexity. You have to be careful that this doesn't become the new monolith, because that's easy to do. We have chosen to use GraphQL, so actually as the layer where our clients, a new part of the client will talk to. And based on that, you can basically say, hey, we're going to add new services to it, and basically say, hey, this is where we keep the real backend services. And at some point, if you say we don't need that proxy anymore, we're just going to put the GraphQL endpoints in the service itself. If you notice, the monolith just became a little bit smaller. So that's kind of the highlight of the presentation. So a few things to take home. Think about the basics you have and the basics you want to have in place for your service, what defines a service in your organization. Secondly, how do you deal with deployment? Can you do it quickly, or is it still a hard problem? Don't have someone raise that ticket again. How do you want to deal with security? Because it becomes more complex as well, because it's not all inside one process. You have to think about, hey, how I deal with testing, and how do you make it easy, and how can I have a decent local dev loop as well? How do you organize your operations? And instead of adding decomposition here as well, I think we should all focus on value. It's not about hey, how cool our tech is. It's important as well, but you want to ship features fast and provide a great experience for your users. That's it. Thank you.